Good morning, everyone. So we, as part of the organizers and being the session chair, I would like to welcome all of you. Kickstarting the day with a very interesting session where Professor Oskar Vafek, who is from the National High Magnetic Field Laboratory and also is at the Florida State University, will be giving us a tutorial on some of the topological and interactions on the systems. So please welcome Professor Oskar Vafek.
Thank you very much. First of all, thank you very much to the organizers for the kind invitation, for the opportunity to be here at this beautiful place, and for putting together this wonderful program. So I was asked to give 2 tutorial lectures. Is that offer still on? Okay. All right, so this is the first one. And it will be on twisted bilayer graphene. It's meant to be interactive. So if you have questions, please do not hesitate to stop me. I actually welcome you to pause me and ask questions. If something is unclear, I will be more than happy to explain. Here's the outline of what I'd like to cover in the first tutorial. I would like to give you a physical intuition for the origin of the narrow bands in the twisted bilayer graphene. We're gonna have a back of the envelope argument for the minimal continuum model. I'll discuss, of course, some of the pioneering experiments which sort of galvanized this field. I will tell you why these bands are interesting. They're not only narrow, but they're also topologically non-trivial. And I will try to make this statement precise. So we'll actually do a calculation in this tutorial. We will use a tool to detect the narrow band topology. The tool is the non-abelian Berry phase. Sometimes it's called the Wilson loops. And I will try to explain how to think about it physically and show you the results of a calculation and its eigenstates. Okay, and so once we understand the nature of our narrow band Hilbert space, this is the space in which the Coulomb interactions play an important role. Given that the bands are narrow, we will then study the effects of the Coulomb interactions. I will show you that unlike in the usual Hubbard model, because of the topology of these narrow bands, the type of states we expect in the presence of strong Coulomb interactions are actually generalized ferromagnets. And try to explain why. And one member of this manifold of states are Chern states. So these are states which have a quantum anomalous Hall effect. We'll see how that comes about. Remarkably, even at strong coupling, there is an itineracy to the excitations. I will try to make this precise. And I will touch upon the observed cascades of transitions. And I will show you how, at least in the strong coupling limit, we can think about it as a cascade between heavy and light fermions. And at the end, I will talk about a new perspective on most of these results, which was advanced by Zhida Song and Andrei Brnovik, and goes under the title of topological heavy fermion model. So I will basically recover most of these results using that picture. I'll show you how that works. So as you can tell, a lot of this is highly theoretical. Obviously, it will be motivated by the experiments. But I think it's a necessary first step to try to understand what's going on in this system. And then, since I was granted a second tutorial, I will make a stronger connection to the experiment in the second one, where we will study specific experiments and both at higher twist angle, away from the so-called magic twist angle, and also closer to the magic angle. And we will also turn on an external magnetic field. It's an important probe that tells us about what's happening in these materials. So we'll study it in the presence of an external magnetic field, in the presence of an external strain, and in the presence of Coulomb interactions. So this is sort of to set the background for us to be able to make a connection to the experiments. So if you imagine placing two honeycomb layers on top of each other, so one of them is in the blue, one of them is in the red, and then you twist them relative to each other by some small angle. The type of angles we are going to be thinking about are of the order of 1 degree, although it can be a little bit larger or a little bit smaller. We're going to see a pattern that you can see by naked eye, the Moret pattern, which happens on length scales which is much longer than the underlying carbon-carbon distance of our honeycomb carbon lattice. And so the smaller this angle, the longer is this so-called Moret period. Okay? Now, in particular, the triangle lattice spanned by this Moret structure will have at angle of order 1 degree, length scale of order 14 nanometers. So that's much longer than the distance between the carbon atoms, which is of the order of an angstrom, maybe 2 angstroms. And so this new supermodulation will now act as a periodic potential, and this periodic potential is going to scatter the Dirac electrons which live at the corner of the Brillouin zone of each of the carbon layers. Okay? So we will no longer just have a monolayer graphene Dirac electrons, but these Dirac electrons are going to Bragg scatter off of this new potential, and they're going to form mini-bands. Okay? And then these mini-bands, in principle, will be separated or could be separated from each other by gaps. And if that's the case, we can then use field effect transistor to take the electrons in and out of these narrow bands and fill them, because the electric fields necessary to do that are accessible before a breakdown of any dielectric that you would need in this setup. Okay? And so that we can now do reversibly, unlike in many materials where you, in order to change the concentration of the electrons, you have to change the chemistry, you have to introduce some dopants or something like this. Here we have the advantage of being able to reversibly add or subtract electrons. All right. So at the cartoon level, what should we expect in this case? All right. So think about the blue hexagon here, the large blue hexagon here, as the Brillouin zone of the bottom layer that I just showed you in the previous slide. Okay, and that Brillouin zone has Dirac points which sit in its corner. So I mark this one by K1. There will be its time-reversed partner in the other so-called valley. Okay, it will be minus K1. Now, the second layer was twisted relative to the first layer by an angle theta, and therefore the Brillouin zone of that layer is also going to be twisted relative to the Brillouin zone of the blue layer. Okay? And so its corner is going to therefore fall onto this point, which I labeled by K2. Okay? So now imagine that these two layers were completely decoupled. So the electrons could not hop from one layer to the next. Of course, physically they do, but we can imagine turning that coupling off. What would we see? Well, in that case, we would just see a band structure associated with each of these layers on its own. So in the vicinity of this point K1, we will see a dispersion that would look something like this blue, where there will be no avoided crossing here. This would just continue going through. There will be a Dirac cone there. Okay? So if we, in particular, if we move along this line that joins K1 and K2, we would see this type of dispersion. Okay? Now, similarly, if we were to look at the dispersion associated with the red layer along the same line, it will also just have a Dirac dispersion. And these two dispersions are going to touch, and they're going to cross at this point. And the energy scale associated with this is simply the slope which of these lines, which is the Fermi velocity, and then the separation between these 2 points. Okay? And this separation is itself set by the twist angle. So the smaller the twist angle, the closer would these 2 points be together. So that's one energy scale in the problem. Okay? But then, of course, the 2 layers aren't decoupled. There is tunneling between them. That's why interesting things happen for the moire. And in that case, this what used to be crossing turns into an avoided crossing. Okay? And there's an energy scale associated with that as well, which we're going to call W. There are actually 2 different W's that will show up in this lecture, but for now, let's just think about it as one energy scale. Okay. And of course, the same thing is going to happen from the bottom here. And so now, imagine for a second a thought experiment in which we hold the twist angle fixed, and we can somehow tune the strength of the interlayer hopping. I'll actually show you an experiment which does this. But for now, just imagine it happening. Well, what's going to happen is that the avoided crossing is going to get larger and larger, and you're going to push on this band from the top, and you try to push it down. And similarly, the avoided crossing here is going to get larger, and you're going to push on this band from the bottom. And at some point, you see, if you have these energy scales matched, you have an opportunity, in principle, to flatten out this band. Okay? Now, whether this happens or not is not obvious. One has to do a calculation, but that's the intuition for this. Okay? So, of course, you can also do it the other way around. You can hold the interlayer tunneling fixed. That's set by chemistry and ambient pressure, and then tune the twist angle. And as you tune the twist angle, you're going to move, you're going to change the distance between this K1 and K2, and therefore move this energy scale until you find the value at which they are comparable, and you obtain this flattening. So you can control either W or VFK theta in principle. Okay? Of course, in the experiment, what you typically control is VFK theta because you control the twist angle. So that's the intuition. And so we should expect one dimensionless ratio to control whether we are at the magic angle or not. That dimensionless ratio is this interlayer tunneling to the energy that sets the crossing between these 2 bands. Now, as I said, the separation between the 2 Dirac cones is controlled by the twist angle. Now, in principle, the interlayer tunneling is controlled by the pressure. So if you apply an external pressure, then the interlayer tunneling would be larger because the orbitals can overlap better between the 2 layers. Okay, so VF is nominally fixed in this material, although Coulomb interaction actually does renormalize the Fermi velocity. So in principle, if you have a control over the dielectric environment in which this system is embedded, then you have some control over VF, but people are not doing that experimentally right now. So experimentally, you typically control the twist angle, and sometimes you control the interlayer tunneling. All right, so that's the intuition for why you may end up with flat bands. Now, we can do better than just cartoons. So this is back of the envelope argument. We can do better than the cartoons. And the minimal continuum model that is used in studying the twisted bilayer graphene is written out here. So let me walk you through various terms. This also often goes by the title Bissesser-McDonald model. So in each valley, so for each Dirac cone, you would write a 4x4 differential operator Hamiltonian. So the first 2x2 block here and the second 2x2 block here, these are just massless Dirac particles. Okay, so sigma here is Pauli matrix, and there are 2 of them. Let's say sigma x and sigma y. P is the momentum operator, and VF was the slope that I showed you before. Okay? So if it wasn't for the Moret potential, this off-diagonal term T of R would be set to 0, and then you would just see these 2 decoupled Dirac cones. Now, in this particular setup, I chose to move one of the Brillouin zones so that the offset between them doesn't show. But that's just a simple unitary transformation that you can undo if you wish. All right, so these two terms therefore describe the two Dirac points from the two layers. Now, in the presence of the tunneling between them, we have this 2x2 matrix that sits on the off-diagonal, which is itself parametrized by two energy scales. One is the so-called W0, and one is so-called W1. So physically, W0 corresponds to tunneling through the so-called AA regions. Okay? So if we go back to this picture, there are regions in real space where you see these honeycombs are sitting on top of each other. These are called so-called AA regions because you have locally AA stacking. Okay? And there are other regions, for example, over in this region over here, where it's more like AB stacking. And then there's a corresponding region where it's a BA stacking. So in this Hamiltonian, the interlayer tunneling through the AA region is parametrized by W0. And then the interlayer tunneling through the AB region is parametrized by W1. Now, if it wasn't for a relaxation effect, which I'm not going to discuss in this first lecture, but I will discuss in the second lecture, these two parameters would be the same. And in the original paper by Bissett and McDonald, they were actually set to the same value. Now, it turns out that this material actually does relax structurally in that the AA tunneling, so the AA regions are energetically a little bit more expensive than the AB regions. And because of that, the AA regions shrink relative to the AB regions. And at least one of the effects of that is not the only effect, but one of those effects is to make the interlayer tunneling through the AA region smaller than the interlayer tunneling through the AB region by about 70%. So this would be about 70% of W1. Okay? But there are other terms which I will discuss in the next lecture. All right. And so in principle, we have another dimensionless parameter in this model, which is the ratio of these two interlayer tunnelings, W0 divided by W1. And at least as theorists, we can play around with that dimensionless parameter as well. Okay. Now, so this is going to be the model that we're going to adopt for the first lecture and study the bands that it gives rise to, and then what happens when we turn on interactions on those bands. This can be improved upon. One can actually expand this to higher order in gradient expansion, include the relaxation, etc. And it will make some changes in the results, which I will show you. But this is still the leading order term you would write down to proceed. All right, now this Hamiltonian has a number of important symmetries. And these symmetries will play a role in our discussion, so I would like to go over them a little bit in detail. So remember, so far, this just describes one valley. This is, let's say, valley K. The other valley you can simply obtain by time reversal symmetry. So you complex conjugate or apply twofold rotation around the z-axis that will take you to the other valley. So it's enough for us to discuss the symmetries in this specific valley. We can obtain the rest by time reversal. Very good. So that's right. That's exactly correct. So this Q naught is what I called delta K over here, is this delta K. So that's where exactly, so the angle shows up primarily there. That's the biggest effect. Is that this Q naught, Q1, Q2, which are showed here, will be affected by the twist angle. So that will affect the Moret potential. Okay. Now there's also this strange-looking term, which is sigma theta. So the angle nominally also shows up there, but it turns out that it's a secondary effect. So what this means is that you take the Pauli matrix vector sigma x and sigma y, and then you rotate it in the Pauli space out in the z direction by a tiny angle theta. So in the original paper, they actually included this rotation of the Pauli matrices. But it turns out that if you set up a systematic gradient expansion for this is actually a higher order term. And since the higher order terms were dropped, it is actually legitimate to drop this term at this order. All right. Any questions? Any other questions? Yes, please. Yeah, so as I said, at this point, just think of it as some version of it, maybe an average or something like this. It's not very important which one of them it is, but if you set W0 to 0, it would have been W1.
Okay.
Okay.
Because like, I think when W0 and equal to W1, then it doesn't gap out, right?
So if you set W0 equal to W1,
yes,
it will not remove the gap between the narrow bands and the remote bands. That's correct. It will still flatten out the band though. That's the key effect. I want to basically give you an intuition for why this band may end up being flat at the end of the day. Okay. And that argument still goes through in that case. But you're right. Any other questions? So this Hamiltonian has some important symmetries, and so one of those symmetries is there if you ignore this small twist angle in the Pauli matrix rotation. So what is this symmetry? I can actually maybe write it down since we have a blackboard. So this is so-called particle hole symmetry, and you can obtain it by acting with the Pauli matrix Y, this I is not super important, in the layer space. Okay, so that's the space that acts between this part and this part, and then you take R2 minus R. So when I acts on some function of R, it turns it into a function of minus R. Okay? So you can check that if you try to apply that to this Hamiltonian, and you ignore this rotation of the Pauli matrix, the entire Hamiltonian will stay in the same valley, but it will reverse its sign. So if you then apply this transformation on HBM, okay, and then you have, this will become minus HBM, modulo this tiny little term theta. So let's see how this would work, for example, for the Dirac piece. Okay, so you take R2 minus R, so that will reverse P, okay, and then you're going to swap the layers. But if you ignore this little theta, then this piece is the same as this piece. So you would just change sign of that term. Now it's a little bit trickier to see for the off-diagonal term, but trust me, what's going to happen is that the I mu y, this piece, is going to swap the T dagger, put it up here for T, and put a minus sign in front of it. And then, if you take R2 minus R with this I, then the T dagger of minus R will just simply become T of R. And so the entire Hamiltonian will change sign. Okay? And this symmetry is there regardless of the ratio of W0 and W1. And it was noticed by Leon Balance's group and by Andrei Bernevik's group. And this will play a role in what we discussed. Now, this symmetry is not exact, as you can already see. If we were to include, for example, this rotation of the Pauli matrix, this symmetry is only approximate. But these people checked how close this symmetry is to being exact at the level of the wave function. So for example, they took a wave function of the solution of this Hamiltonian at a particular energy, and they compared it to the wave function at the minus energy. And of course, because there's an R2 minus R, you also have to change K to minus K. And they noticed that to less than 1% accuracy, the error is less than 1%. So it's a very, very small error that you would commit by introducing this term. So this symmetry is almost exact. In fact, what they say in that paper is that that symmetry is just as good as if you ignored spin-orbit coupling in graphene, which almost everybody does, although in yesterday's talk you heard about maybe bringing spin-orbit coupling back. So, for a lot of the things that I will show you, I will assume that this particle-Hall symmetry is present, okay? But it's not exact. There's an additional symmetry that this Hamiltonian has, and that's so-called C2YT symmetry. C2ZT. And now notice that this particle-Hall symmetry acts within a valley. It doesn't take you to the other valley. And in this symmetry, it also acts within a valley, but the way it works is that you perform a twofold rotation about the out-of-plane axis, so that's 180-degree rotation. They would take you from valley K to valley K prime, and then the time reversal symmetry brings you back, okay? And so you're gonna change, because it's a C2 symmetry, you're gonna change R to minus R, okay? And then this will complex conjugate, and at the same time, you also have to use Pauli matrix X. So this would be something like this, and then complex conjugation. So the Pauli matrix X is there because if you perform a twofold rotation, you're gonna swap the sublattices. Okay? And this Pauli matrix over here that acts in a sublattice space, A and B sublattice of the honeycomb lattice. So you can check that this symmetry is also a symmetry of this Hamiltonian and acts within a valley. And also, that's also a very important symmetry in this business. Okay. Now, the original derivation of this was in momentum space. There is a very nice paper by Leon Balance where he provides an alternative real space perspective on how to derive this, and think of this as an effective field theory. And we use this perspective to build upon this and set up a systematic improvement to this Bissinger-McDonald model, in which we can treat an arbitrary smooth lattice deformation, including twist angle inhomogeneity, and we can go beyond just the leading order terms. And for those of you who are interested, there are two papers. This is the first of the two papers, and the reference to the second paper is over here. So if you want to see how to derive this or how to go beyond this, and how to do this from microscopics, I refer you to this paper. Okay, so this is going to be what we're going to use throughout the rest of this talk. All right, so now to convince you that you actually get narrow bands out of this more sophisticated model, where you're actually solving a block problem, I'm going to show you a little simulation in which I'm going to continuously change the twist angle. We're going to start at a fairly high twist angle, 3 degrees. And then we're going to take this cut through the Brillouin zone. Okay, that's on the x-axis here. The y-axis is the energy, and I did not label it in real units on purpose. Now, as we change this twist angle and make it smaller, then of course the Moret period gets longer, and therefore the Brillouin zone gets smaller. So instead of continuously rescaling, instead of continuously showing you things on a smaller and smaller scale, I will continuously rescale so that this is set fixed. Okay, so the x-axis here will not change, and then as we change the twist angle, you will see what happens to these Moret bands. So let's see if this plays. So as you lower the twist angle, you see the bands are indeed pushing against each other. And at some point when this approaches about 1 degree, they become extremely flat, right about now, and then they broaden again, okay? So it is indeed true that you can really flatten out these bands using this effect, okay? And this is what they notice in this famous paper. All right, so once you have flat bands, then of course, it's an interesting question to ask, what happens when you turn on Coulomb interactions for the electrons which move within these flat bands? Because the kinetic energy has essentially been quenched, at least within this picture. And so then the Coulomb interaction should be the dominant decider on what phase of matter the electrons take. Now, this is the famous, this is a graph from the famous paper, from the famous experiment from the MIT group, where they took these twisted bilayer graphene devices at a twist angle of 1.16. And what's plotted here on the y-axis is a two-terminal conductance, and on the x-axis is the carrier concentration. So remember, I told you that if you have a back gate and top gate, but it's enough to have back gate, you can change the carrier concentration in the system. It's better to have both. And then you can reversibly go from here to here. So this would be the so-called charge neutrality point. Okay, here you're doping holes, here you're doping electrons. And what you notice is that, first of all, the two-terminal conductance drops here to essentially 0 in this region and in this region. And these regions correspond to the gaps, to simple band structure gaps that separate the narrow bands from the so-called remote bands. Okay, so there's nothing surprising about these insulators. They can be explained using single particle physics. Okay, this one and this one. What's surprising is what happens in between. Okay, so in particular, near the filling factor -2, which would correspond to 2 holes relative to the charge neutrality point per Moray unit cell, they discovered that there is an insulating-like behavior, at least at higher temperatures, and that's flanked by a superconductor. And then, of course, that made a lot of people very excited about this. There's a similar thing happening at filling factor 2, and there were already then signatures of correlated phases or correlated phase at filling factor 3, so odd filling factor. None of these would have happened in the single particle picture. This is a follow-up experiment from Andrea Young and Corey Dean's group, in which they did something very nice. Namely, they took a device whose twist angle is away from magic. Okay, so this is 1.27 degrees. Remember, at 1.27 degrees, the bands, they might have been isolated from the remote bands, but they were not flat yet, okay, in that little movie that I showed you. And indeed, they see a dip at the charge neutrality point, but it's likely just Dirac points. You would expect a dip in the conductance from Dirac points, and that's the gray curve. Other than that, you're not really seeing much. Okay, this certainly doesn't drop to 0, okay, like it did in the previous experiments. And that's presumably because the bandwidth is still too large and the Coulomb interactions are not strong enough to cause insulation, like it did at the magic angle. However, when they applied an external pressure, they're presumably changing the interlayer tunneling, they're changing the W's, and so even though they are away from the magic angle at the ambient pressure, once they increase the interlayer tunneling, they can flatten out the band, and that's the blue curve. And so now they start seeing insulators at filling factor -2, filling factor +2, and the 3 is very clear as well. Now you just start seeing signatures at 1 as well. Okay, and then there are many other experiments on this. This is the data from Dmitry Afetov's group, where they also saw insulators at almost every integer, not quite, but almost every integer, and superconductivity for quite a few doping windows in this phase diagram. So this is what made a lot of people excited, and so this is the motivation for studying these narrow bands and what happens when you turn on interactions. All right, so now that we have these narrow bands, we have an effective Hamiltonian that we are solving with its own wave functions. We would like to understand whether these bands are topological or not. So how do we do this? I should first stress that when I say topological, I do not necessarily mean that these bands carry a finite Chern number. And in fact, they cannot. And the reason why they cannot is because of this C2YT symmetry that prevents it from having a finite Chern number. So if they are topological, they have to be topological in a different sense. So for example, you probably heard about the Z2 topological insulators, of Kane and Melly. you know that they preserve time reversal symmetry. And because they preserve time reversal symmetry, they cannot carry finite Chern numbers. But nevertheless, they're still topological. Okay? So how do we detect this topology in our setup? So one nice way to do that was introduced by these gentlemen, is to study essentially a eigenstates or an eigenvalues of a position operator when we project this position operator to the Hilbert space of interest to us, so subspace of interest. So for us, that subspace will be the narrow bands. Okay? You'll see exactly why it makes sense to think about the position operator. Of course, if I ask you what are the eigenstates or eigenvalues of a position operator in free space, you should say they are delta functions. Okay, Dirac delta functions, and every position is an eigenvalue. But that's not true if I do not allow you to use the entire Hilbert space. If I tell you you're only allowed to use a subspace of that, then of course you cannot make a perfect delta function if you restrict your full Hilbert space to a subspace. And similarly here, the role of that restriction is this projector over here. Now the reason why this is not just an ordinary position operator, by why it's a phase, is because we would like to use our block states. And our block states have periodic boundary conditions over some large system. And if we just put a position operator in here, the position operator is going to violate these periodic boundary conditions. So it's actually nicer to work with this object, which is almost like a position operator, but it satisfies the periodic boundary conditions of our total system. Okay, so think about this as basically diagonalizing, let's say, X or Y, okay? Subject to the constraint of being in the narrow bands. So how would we do that? Well, this is our Brillouin zone. It's spanned by this G1 and G2. K1 and K2 are some numbers between 0 and 1, which will locate our place in this Brillouin zone. So now, let's say that we choose our delta Q here to be this tiny little vector in the X direction that is something like 2 pi divided by the system size in that direction. Okay, so in that case, what's going to happen is that this operator is going to mix block states along this line, which are separated by delta Q. Okay, and it's not going to mix states along this G2 direction. Okay, so if we want to diagonalize this operator, we can, and of course, in the thermodynamic limit, we're going to be thinking about this delta Q as going to 0. So if we want to diagonalize this operator, we're going to seek eigenstates of this form. We're going to superimpose block states along this direction. So that's exactly what this says. And these alpha are the superposition terms, admixtures. Okay, and so now this is a fairly simple exercise. You act on this superposition with this operator, and you get a relation between the various amplitudes over here, and the term that this B here corresponds to a band index. So since our narrow band contained really 2 bands, our band index B is going to go between 1 and 2. Okay, and this J here that just simply labels these dots. Okay. And so the overlap between the neighboring block states here, at least to be precise, the periodic part of the block states, that overlap, I'm going to call this matrix a lambda, and it's a 2 by 2 matrix because the B and B prime run between the 2 bands, 1 and 2. Okay. Now the J here is telling us which of these bonds we're computing this overlap for. All right. And then, as you see, the wave number along the G2 direction stays the same. So K2 is the same here as here. What's really changing is the wave number along the G1 direction, the delta Q piece. Okay, so this we can compute. We can compute this numerically, fairly straightforwardly, if we have the Bloch wave functions. That gives us these 2 by 2 matrices on every link. And then, again, it's a fairly simple exercise to solve for the eigenvalues of this operator. And if you do that, you discover that what you need to diagonalize is a product of these matrices over these links. And this is also sometimes called the Wilson loop for the reason that you will see. All right, now in the limit where this delta Q goes to 0, this object becomes unitary. It's a unitary 2x2 matrix. And we're going to be looking for eigenvalues and states of this unitary operator. And this is going to give us something like the most squeezed wave function in the x direction. Of course, we expect this wave function to be delocalized in the perpendicular direction. All right. So this can be connected to the so-called non-abelian Berry phase. So if we look at this overlap in the limit of small delta Q and expand to leading order, we're going to obtain this. But then, of course, we know that we can move the derivative on the front, so that gives us a minus sign over here. And this is also a complex conjugate of this. And so this is actually an anti-Hermitian term. And so in the limit of small q, we can also write it like this. Okay, we're exponentiating this matrix. And so this AB is a Hermitian 2x2 matrix. Another way to write this is as a path-ordered integral as this. Okay? And this is often called the Wilson loop. This is our unitary operators. And so its eigenvalues are going to be phases. How should we interpret those phases? Well, they are basically telling us the average position of our localized states in the x direction. Okay? And I'll show you this. Now, in practice, what we do is we, of course, have to keep this delta Q finite. We have to discretize our K-space. And so then this overlap matrix is not exactly unitary. So what you do singular value decomposition. And you notice that this matrix, the diagonal matrix with the singular values, is very close to 1. And so you just remove that and you turn it into a unitary matrix. Okay? And this is what you study. Okay, the numerical advantage of this method is that the W does not depend on the choice of the phase of U. So when you solve this on a computer and you're not fixing the phases of your wave functions, the computer is going to randomly assign a phase to your block state. This procedure doesn't care about that random phase. That's the nice thing about it. It's gauge invariant in this sense. So if we do this for our problem, this is what we find. So let's focus on this graph first. So this already shows you the eigenvalues of this 2x2 unitary operator, which you should think about as sort of average positions of the localized state in the x direction and extended in the y direction, as a function of the good quantum number along this G2 direction. Remember, the G2 we never mixed along the G2 direction. We only mixed along the G1 direction. Okay, so what we find is that, okay, it's a 2x2 matrix, and so it's going to have 2 eigenvalues, and we notice that they come in pairs. So the eigenvalues of W come in complex conjugate pairs, which means the phases are opposite between them. And as we change this good quantum number K2, we see that one of them winds in the negative direction, so it goes from positive to negative, and the other one winds in the positive direction. It goes from negative to positive. Okay. Now, this should remind you of something. It should remind you of what you saw for Landau gauge Landau levels in your quantum mechanics class. As you change the momentum of the Landau gauge wave function along the delocalized direction, the wave packet drifts to one side or the other depending on the sign of the magnetic field. So what this is telling us is that this Hilbert space made out of the 2 narrow bands is sort of secretly decomposed or made up of 2 states which have opposite Chern numbers. One of them is Chern plus and the other one is Chern minus. And that's a signature of topology. Okay? And we can study this as a function of the ratio of these 2 tunneling amplitudes. So this is just for theoretical interest. If you set it to equal to 0, this so-called chiral limit, then the Wilson loop shape looks just as I showed you. It certainly winds and it winds regardless of the value of this ratio, but the shape of this Wilson loop actually changes as you go closer to the ratio equal to 1. So in particular, you start seeing this flat region in which even though you're changing this wave number, your wave packet is sort of stuck there. And only at the end, it remembers that it's actually a churn state, and then it picks up this piece. So this actually tells you something about the way this so-called non-abelian Berry curvature is distributed throughout the Brillouin zone. So closer to the more realistic case, you see that Berry curvature is mostly, you can't see it from this plot, but this is what this means. It's mostly near the so-called gamma point. Okay? And further away, it's flat. And we will see this is actually important for this so-called topological heavy fermion construction. So in any case, the point of this plot, of these plots, is that regardless of the value of this ratio that you choose, either in the so-called chiral limit or away from it, the bands are topological. They can be decomposed into a churn plus and a churn minus bands. Okay? But the details of how the non-abelian Berry curvature is distributed actually depends on this ratio. That's the upshot of this point. All right, so this is very similar to what would happen in a Z2 topological insulator. If you were to do this exercise for Kane and Melly model with in a Z2 non-trivial phase, so you have two bands separated by a gap from two other bands, and then you project it onto the Hilbert space of the lower two bands and plotted the Wilson loops, they would look like this. Okay, they're decomposed into churn plus and churn minus. Okay, so what do the eigenstates look like? So I plotted them here on the left. You see there's a blue branch which winds to the right, and there's a red branch which winds to the left. So they are delocalized in the y direction. Okay, they are localized in the x direction, and as you change the good quantum number along the G2 direction, these things drift around like this. Yes, please. The two narrow bands.
And it's actually two, there are only two.
Yeah, so in each valley and for each spin, there are two. So think about the argument I gave at the beginning for when you have these two Dirac cones which come from the top and bottom layer and then they cross and then they get isolated. You see, you're gonna get one band from just above the charge neutrality point, one band from just below the charge neutrality point, connected through those two Dirac points. And then they are separated from the rest of the spectrum.
You consider one valley, one spin.
Exactly. You're welcome. Any other questions?
You have time reversal symmetry. So you mean even though churn number will be 0, you can calculate the Wilson loop, and
Yes.
that will give you the signatures that you get by calculating the indices.
Yeah.
Okay.
Well, I'm not using, you can use indices if you like. This is not quite Z2 TI indices because here the protecting symmetry is not time reversal. I will discuss which is the protecting symmetry. In a Z2 TI, it is the time reversal symmetry. So there you could use that trick, okay? But if you didn't use that trick on a Z2 TI and you ask for what do the Wilson loops look like, that's what they would look like for Z2 TI as well. One would wind one way, another one would wind the other way, and they would cross. Okay, that's my point. But the symmetries which protected here are not time reversal symmetry. So it's not the same in that sense as a Z2 TI.
I guess what I was asking is there a way to detect the topology there using the Wilson loop?
Yeah, that's what I just showed.
Okay.
I just detected the topology by seeing that the Wilson loop winds. Okay, any other question? Arun, you had a question? Good, very good. So these sites are the AA sites. Okay, so the peaks in the density of states are on the AA side. So very good. So this is another point I wanted to make is that yes, these things look sort of like Landau gauge Landau levels in that they drift one way or another depending on the good quantum number along this direction, but they're not simple Gaussians. Right? They clearly have a richer structure in this direction than a Landau level would. Okay, so and of course that's going to be very important when we compute the Coulomb matrix elements, etc. Okay? But the topology of the bands is there. Okay. Any other questions? Yes, please. How do you measure W's at the Dirac point? All right, so there isn't any direct measurement of the W's that I'm aware of. What there is a STM measurement of the size, the relative size of the AA to AB regions. So there's some estimate from there that this is maybe 0.7-ish. But there are other terms in this Hamiltonian, which I stressed at the beginning, which are beyond the minimal continuum model, which will come in and they will not change the topology, but they will change the shape of the bands and how they are isolated from the rest, etc. No, so remember what this object is. It's a superposition. It comes from superposition of block states along this path, which is really a non-contractible loop. So you're mixing in various k points along this direction, but you're not mixing in k points along this direction. Therefore, you still have a good quantum number along here. But these are all mixed up now. Does this make sense? All right. So hopefully I convinced you that these bands are not only narrow, but they're also topologically non-trivial. Yes, please. Correct. So each band, strictly speaking, will have a zero turn number. It will have zero Berry curvature because of C2ZT, I'm sorry. Okay? Per valley. Exactly, per valley. So you have two bands, and basically what this is not exactly like that, but the way to think about it is that you see C2Z is going to take you from one valley to the next. Time reversal brings you back. So now you are per valley, and time reversal is a spinless time reversal, so it's basically complex conjugation. So it's almost like saying that your states are real. If you have real states, you don't have Berry curvature. But you can have this non-abelian Berry curvature. So that's how you would tell. Okay. All right. Okay, so let me not belabor this point. The reason why the Wilson loop eigenvalues are opposite is because of the C2ZT symmetry of the continuum model. So in particular, because one of our eigenvalues has a non-zero imaginary part, its complex conjugate is also an eigenvalue. And so this basically just means that the eigenvalues of W are complex conjugates of each other. Another way to do it or to show it is to then take our localized states that we just constructed. They can be made to have smooth gauge throughout the Brillouin zone, construct block states out of this, and then write our kinetic energy in that basis. It's going to contain, let's say, Pauli 1 and Pauli 2 in this basis, and therefore you can study the winding of these N1 and N2, and then you can check that the winding number here and here is the same. And this is a point that was made early on by Ashwin's group in collaboration with Senthil's group, that these two Dirac points have the same winding number. Now, if one wants to be kind of pedantic about this, there are actually still two possibilities. The determinant of this Wilson loop can be plus or minus 1 for these two bands. The case that we are dealing with here happens to have a determinant equal to plus 1, but there's another possibility, in principle, that this determinant would have been minus 1. And since they have to be complex conjugates of each other, the only way you can do that is that they are real and 1 and minus 1. So in other words, the complex conjugation takes you between 1 and 1 and between minus 1 and minus 1. And in that case, the bands would actually be trivial. And for those of you who are interested in this, I can give you an example of a case where that happens. Interestingly enough, there is a solution with interactions with Hartree-Fock that's in this paper with Fangjie and Andre and Nicolas' collaboration, where we indeed find that in the so-called period 2-stripe state, despite the fact that it preserves C2T, it actually has a trivial winding. But anyway, this is just a side comment. I don't want to belabor this point. So, okay, so now I kind of stressed the importance of this symmetry. By the way, the particle hole symmetry is not important for the topology that I just showed you. This Wilson loop winding would be there even if the particle hole symmetry was broken in the continuum model. If you bring this particle hole symmetry back, however, it will turn this topology from so-called fragile to stable. So again, I don't want to belabor this point or get too much into this, but if you're interested, I'm happy to tell you about later. So the important thing for us right now is this C2Z symmetry. But you see, it turns out that you can say, well, the C2Z symmetry is not exact. And that's true. For example, if you were to consider this particular structure, this is obviously not at magic angle, such that we twist, so we start with the AA stacking, and then we twist about this dimer, then this commensurate structure would have a C3 symmetry. It would have a C2Y symmetry, so that's a twofold rotation about the y-axis that goes between the dimer. Here you can kind of clearly see that the blue and red are going to get swapped under that rotation, but it misses the C2X symmetry. See, this red doesn't have a partner over here. This blue doesn't have a red partner over here. So in this structure, the C2X symmetry, strictly speaking, is absent. Now, if C2X is absent, but C2Y is present, because C2Z is a product of C2X and C2Y, you will not have C2Z T. Time reversal is, of course, present. So the question is, does all of this go out of the window the moment the symmetry is no longer exact? And the answer is no. And the reason for that is because this is really an emergent symmetry. So in other words, what I showed you is true when you are able to resolve these atoms. In other words, when the size of the when the size of the real space unit cell is comparable, larger but comparable to the size of the atomic spacing. But the moment you go to these small angles, you see this sort of merges into one almost a continuum like image. And in fact, if you were to do a brute force tie binding calculation on a model that contains something like 10,000 sites. Okay, so if we were to do this calculation on a tie binding lattice, so no continuum model, no Bicester-McDonald at all, you just do a brute force tie binding calculation with 10,000 or 11,000 atoms. This is the type of band structure you would find for this specific commensurate angle. M and N are the integers for those who want to know the details. So this, because it's a tie binding calculation, it automatically contains the two valleys. Okay, so you can see you have 4 bands here. Okay, that's because the two valleys are on top of each other. Now, the reason why the gamma M dispersion is split, but the MK prime dispersion is not, is precisely because these two Brillouin zones are related by time reversal or C2Z. Now, the key point is what's going to happen here. So you see, from this resolution, it looks like we have double Dirac touching here. Okay, because remember there are 4 bands here, and this would then correspond to the two valleys, the Dirac points of the two valleys being on top of each other and basically not hybridizing. However, if you actually were to zoom in, so first of all, if you were to zoom in here, there would be a true touching. But if you were to zoom in to this point, there actually is a tiny little splitting. Okay? And that splitting corresponds to the intervalley tunneling. So the tie binding model actually does have the intervalley tunneling in it, unlike the continuum model. And so this is the amount by which you are breaking this C2Z symmetry. Okay? And so most of us ignore this effect. Okay? Whether this is important or not, it's unclear at the moment, but it is really a much subleading term. Okay? So we consider the valleys as being completely decoupled. But it's not exact. It's an emergent symmetry statement as well. All right. So that concludes the band structure part. So now on to the electron correlations. So the problem that we would like to study is a problem in which we have the kinetic energy that's described by the continuum Hamiltonian. So this is our 4x4 differential operator sitting here. This is its other valley partner, complex conjugate, due to time reversal symmetry. And this chi organizes our low energy degrees of freedom or Dirac degrees of freedom from the two layers and from the two valleys. And in principle, we can expand this in terms of the exact eigenstates of this continuum model, psi. So this psi here is a 4-component object. The two valleys are related, so you can actually write the wave functions in the other valley in terms of the wave functions in the valley k. Now, the Coulomb interactions will come in through a term that looks like this. The delta rho here is a density fluctuation operator. It looks something like this. It's a chi dagger chi minus this anti-commutator that gives us the background value. And the V is a Coulomb interaction. Now, in general, in these experiments, the twisted bilayer graphene is sandwiched either from both sides or from one side with HBN. And then in addition to that, you have gates. And so there will be image charges in the gates. So this Coulomb interaction, in principle, is not just an ordinary 1/r Coulomb interaction, but it will contain corrections due to the dielectric environment and due to the gates. Okay? But you should think of this as a repulsive Coulomb interaction. Okay, and there's this identity, this is this very nice identity that you can rewrite this anti-commutator that's sitting over here through the sum over all the exact eigenstates below our cutoff energy, EC. So the big picture perspective on this is what we would like to do is we would like to find what is the effective Hamiltonian, interacting Hamiltonian within these narrow bands in some systematic fashion. One way to proceed is to just simply project all of the interactions that I showed you on a previous slide onto the wave functions of the narrow bands that we studied previously. And that has been done in almost all papers. But the systematic way to do this would be to set up a Wilsonian renormalization group-like treatment, where you start with everything in principle. Okay? And then you start integrating out the high energy bands one by one until you arrive at the effective Hamiltonian in the narrow band regime. And we actually did this in this paper. Now, the reason why this is possible to do is because the Coulomb interactions in monolayer graphene are not strong enough to open up the gap at the Dirac points. So what we would say is that they are perturbatively irrelevant. Under the renormalization group scaling, they shrink. And so in this high energy regime, we expect the Coulomb interactions to still be perturbative. They're certainly not perturbative in the narrow band regime, but for the rest of the states, we expect them to be perturbative. Now, the interlayer tunneling, the W's, are perturbative above an energy scale set by this interlayer tunneling. Okay? So up here, we have an opportunity to perform an analytical calculation that will integrate out these thousands of bands out here without using numerics that we can justify using perturbation theory for Coulomb interaction and perturbation theory for the interlayer tunneling. And there's a second stage of our RG treatment where we do not touch the narrow bands, but we are below the stage one. So we are now, the cutoff on this stage is of order the interlayer tunneling, but before we reach the narrow bands. So the cutoff will be somewhere over here. And here we still treat the Coulomb interaction as perturbative because of this gap, but then we treat the interlayer tunneling as non-perturbative. In any case, this program can be carried out. This is just what I said. And then in the final step, we find that the Coulomb interactions are still much larger than the residual bandwidth. And then in this regime, we then treat the Coulomb interactions as non-perturbative. And so what we're going to do in the rest of this talk is study this so-called strong coupling limit. Okay, so let me show you a result of a DMRG calculation. So for those who don't know, this corresponds to density matrix renormalization group on a simplified model in which we assume just one valley and one spin. But then we consider a half-filled state. Okay? So the system still has a choice of what it's going to do. And what we find is that as we tune this dimensionless ratio, W0 over W1 from the so-called chiral limit, to closer to the realistic value, we find a phase transition between a state which breaks this C2YT symmetry and is indeed just a Chern state. Okay? In other words, in this case, it mixes the two bands in such a way that it polarizes all the electrons either to the +1 Chern band or -1 Chern band. Okay? So, and in this calculation, there's no ambiguity about what the state is here. But interestingly, as we increase this dimensionless ratio closer to the realistic value, there's a collapse of the order parameter for this quantum anomalous Hall state, namely the C2YT symmetry can label our state. And here we find a state in which C2YT is restored, and we have broken either rotation or translations. We have close competition between two states, which are either stripe-like or they are nematic-like. Now, so this is still a toy model calculation because it only considers one valley and one spin. But we clearly see that something interesting is happening near this realistic value of the ratio. Plus, we also clearly see that the topology can be revealed by Coulomb interactions. Here, okay? You can indeed, despite the fact that the original band did not have any Chern numbers, but it was an admixture of Chern plus and Chern minus, the Coulomb interactions can stabilize you in a Chern plus or Chern minus 1 state. Okay. Now, this was subsequently confirmed by more accurate DMRG algorithm from Mike Zolotel's group, where they found basically the same thing. The transition happened at basically the same value over here. This is a little bit busy, but they had various order parameters. Upshot of this story is that on this side, this is indeed a quantum anomalous Hall state, just as we found. And then because they could resolve the tiny energetic differences between various C2ZT symmetry preserving states, they could actually tell that this is a nematic as opposed to a stripe state. But when they looked at the energies, they found that their ground state is actually extremely close to this ansatz that we proposed in our paper. So think of this as a close competition between either a nematic or a stripe state in this case. Now, interestingly, because those states preserve C2YT, those states will have 0 Chern number. Okay? All right. Now, there's a beautiful set of experiments. One is from David Goldhaber-Gordon's group at Stanford. Another one is from Andrea Young's group at UC Santa Barbara, where they revealed this topology in a slightly different way. So in addition to what I just showed you, they also aligned the twisted bilayer graphene with the underlying hexagonal boronitride. And when they do that, the A sublattice and the B sublattice of carbon feel different potentials. And because this C2Z symmetry interchanges these two sublattices, they actually explicitly broke this symmetry with the alignment to the HBN. And what that does is it takes your narrow band and splits it in each valley into Chern plus and Chern minus. So now at filling factor 3, you have a choice of where you put the last hole, whether you put it in valley K, the top Chern band, or valley K prime, the top opposite Chern band. And this is precisely what they found. They find that they're indeed polarizing it into one valley or the other, and that the Chern number can be detected directly by measuring the quantum anomalous Hall effect. This is the quality of the quantization of this. So this made it clear to everyone in the field that indeed topology is there. Because notice that you nominally don't have any magnetic field here at all. You're revealing this C2Z T symmetry simply through the sublattice potential. Okay, now in the model that I just showed you, what happens at the end of this renormalization group treatment is that you find that the Coulomb interaction is much, much larger than the residual kinetic energy. Whether this is true in an actual more realistic setup or not, I'm not making any claims in this lecture. It's probably not. This is probably idealized because the minimal continuum model gives you too narrow of a bandwidth, as I will show you in the next lecture. But at least logically, this is where this calculation takes you. Okay? It will show you that the Coulomb interaction within the narrow band is now much larger than the residual kinetic energy. Okay, so then what can you say? Well, let's then ignore this term and bring it back perturbatively. Okay, so now our task is to find states which are eigenstates or ground states of this term in our Hamiltonian, of the Coulomb interaction. And it turns out that this can be done at the charge neutrality point. And the reason why this can be done is because, you see, this is a positive semi-definite operator. If your interaction is repulsive, you can decompose it in various eigenmodes and show that if you have something that's positive semi-definite and you find a state which is annihilated by a positive semi-definite operator, you have found the ground state. Okay? And so in particular, all you have to do is find states which are annihilated by this density fluctuation operator. It turns out that there is a manifold of such states, and it can be accessed either through the Chern states, which I showed you, at least in a chiral limit, or it can be accessed through valley polarized states. Okay? Each of these would be gapped insulators. At even integer filling, the problem is a little bit more complicated, but you can still find eigenstates of this operator, which are eigenstates of this density fluctuation operator. But to show that they are ground states, you have to do numerics. Andre Bernevik's group actually has done exact diagonalization on this and showed that indeed the exact eigenstates are also the ground states for most of the parameters in this model. And so they would also correspond to something like valley polarized states, out of which you then can rotate due to symmetry, which I haven't mentioned yet. And then finally, at odd integer filling, only in the chiral limit, namely when W0 over W1 is set to 0, you can make exact statements. And in that case, the Chern states, just as I showed you before, would be the ground states. Anyway, the upshot of this story is that at least in the strong coupling limit, the generalized ferromagnets are favored by the projected Coulomb interactions. For those of you who studied Hubbard model, that's not what happens. You're used to antiferromagnetism in the Hubbard model. Now, why does that not happen here? Well, it doesn't happen here because the density operator is projected onto much more complicated wave functions of those narrow bands than in the Hubbard model. Okay, so let's see. Am I out of time? Yes, I'm out of time. So let me maybe just stop here and then maybe pick up on this in the next lecture so that I don't overrun my welcome. So thank you very much.
We can have maybe a couple of questions before we take the tea break.
Yeah, I don't have that intuition. But I do have an intuition for why it increases, right? So in other words, the bandwidth first goes to 0, and then it goes back up. So that already, so that you can kind of see, right? The relative, so remember there was this effect of level repulsion due to W, right? And so now this W is larger than the initial energy separation between those crossings. And so it sort of overshoots, you see. Now, the reason that why this eventually goes back and becomes magic angles, I don't have a statement upon. But I should tell you that it's probably of academic interest only as well. And the reason for this is because of the reconstruction. So as I told you at the beginning, the AA stacking is energetically unfavorable compared to the AB stacking. And so as a result, if it wasn't for the elastic energy of distorting the individual monolayer, the AB regions would just grow and BA regions would grow at the expense of the AA regions. Now, this continuum model doesn't assume that at all. The continuum model, actually, the original continuum model just assumed a rigid twist with no relaxation. So now the question is, what happens at the first magic angle? What happens at the next magic angle, etc.? So it turns out that people looked into the various energy scales associated with the elastic distortion of each monolayer and the so-called generalized stacking fault energy, so the energy difference between the AA and AB stacking. Now, so the way to think about it is like this. Imagine there was no elastic energy cost whatsoever. then what you would want to do is you want to make ABBA triangles everywhere. And then these ABBA regions would be separated by extremely sharp domain. Now, you can't do that because the extremely sharp domain is going to cost you elastic energy. But how much elastic energy is it going to cost you? Well, it's going to cost you something that scales with the perimeter of this triangle. But the generalized stacking fault energy saves you something like the area of this triangle. So now when you compare area to perimeter, that means there has to be a length scale in the problem. So people who looked into the actual numbers found out that that length scale is comparable to the length scale of the Moret lattice spacing at the first magic angle. Okay? Such that at the first magic angle, there already is some reconstruction, but it's not severe. So the AA regions shrink at the expense of growing ABBA, but maybe let's say 70%. But once you go to the next magic angle, it's more severe because now the length scale, the size of the Moret unit cell is much larger, so you're saving a lot more on the area. So people who actually did these calculations, including the relaxation, found that the next magic angle and the rest of the magic angle of this minimal continuum model go away. In the limit of very small twist angle, you should think of it that way. In the limit of, let's say, larger twist angle, let's say 3 degrees, you should think of it as basically rigid twist. And now you're interpolating between these two through a crossover that happens roughly at a twist angle that is lower than the first, but is not far from the second. So by the time you're at the second magic angle, the reconstruction is actually severe. So the people who did these calculations, particularly Tim Kaxiras, claim that all the other magic angles are gone. No, the bandwidth is no longer that narrow.
Any further question? Okay, I have one question.
Please.
So, I mean, you shared, you showed 2 or 3 slides. I believe it was from, one of them was the MIT group, where you showed that there were regimes of the charge density where it was superconducting and, of course, again, insulating. So typically in schools and in colleges, we study that superconductivity should also show masonry effect. So how about looking at such aspects? I don't know. I mean, how to?
So in 2 dimensions, you're not going to see full flux expulsion, right? Because it's just a 2-dimensional. You don't have enough currents to shield a 3D magnetic field. But in principle, what people have done, not in TBG but in other systems, is to locally look for diamagnetism. Mm-hmm. I'm not aware of anyone having done that experiment in TBG.
Right.
Now, but it isn't just the transport which convinced people that these things are superconducting. So actually, even in the original paper, Pablo made an argument that near the filling factor -2, where you saw these 2 domes that had a superconductor, and I mean, they called it a mod insulator in the original paper. They no longer call it that way, but there's sort of an insulating region in between. It was actually inhomogeneous. So there was superconductivity was sort of in this background of an inhomogeneous insulator, and therefore it was forming weak links, Josephson-like junctions. They claimed they saw signatures of that already in the original paper. And since then, people are looking for Fraunhofer patterns that would be more directly associated with the phase coherence, which is, I think, what you're asking for.
Yeah.
Additional, more than just transport.
Yeah, more, yeah.
Yeah.
All right, thank you.
Yeah, I guess, yeah, now that there's that too.
Okay, if there are no further questions, let's thank Professor Oskar Vafek.
Thank you.
And